Good, thank you.
Now, a good morning to everyone that has just joined us, and hello to anyone that is watching the replay of this. Welcome to another one of our online learning webinars. This time it's all about masonry stabilisation, what you need to know. I am your host, Andy Ferguson, and today I am pleased to welcome Brian Hindle of Bricktie. We are about to start the main presentation. Now, just for those that are just joining us, if you do want to pose a question over the course of the webinar, the first place I would point you to is just to the chat facility, either on the left and the right hand side. If you're on a desktop, if you're on a mobile, it will just be at the bottom of your screen, just pull up. I would love it if you could say a wee hello if you are just joining us, tell us where you are in the country. If you don't want to use the chat facility to pose a question, there is other ways. You can email me directly at andy@property-care.org. That's andy@property-care.org. Or alternatively, if you are socially savvy, use one of our social media tools. If you're watching the replay of this, you can again just email me directly at the email address I mentioned there, and I will do my best to ensure to try and get that question answered for you. Brian, I can see that it's pretty much bang on 9 o'clock here. It pretty much looks like it's time for us to start the main event. So, masonry stabilisation, what exactly do we need to know? How can we spot potential problems? And why exactly the homes and buildings crack and bulge? Some interesting and big questions there, my friends. And I suppose it's over to yourself.
Thank you very much, Andy, and welcome to everybody. Welcome to Yorkshire. I'm glad you've joined us this morning. As I said earlier, you're a broad church, so there will be something for everyone, I promise you. But basically, we've got a lot to cover. We could cover all this, sections and take a long time over it, but we haven't got that. So be patient, your slide will arrive. Okay, so I'll just take you briefly through what we're going to cover. We're going to look at some cracks. I'll show you some collapses early doors because everybody likes a collapse. But the reason I'm showing you those is just to illustrate collapses that commonly occur due to the handful of defects we get in superstructures that cause them to crack or to fall over in some cases. So we're going to cover that first. Then we're going to go through some basics for our students that are attending. Some basic load paths and things. Can be a bit dry. I'll try not to make it too dry for you. I hope it's okay. We'll look at early indications. This is from a surveyor's perspective. Early indications that we might have issues in the building. And then we're going to look at, again, some more basic things like basically bearing stresses and reducing them to underline the importance of the structure and the material that houses are built from. The fact is, they're very soft materials, and we'll go into that. So we don't want to overstress them or use massive patras plates and things that tend to load buildings up. Then we'll look at some defects and remedies. I'm not going to go massively into remedies because there are plenty of people, the Helifixes, Thor Helicals, Pamties, wherever. There's loads of people who can organise CPDs for you on all the various methods. Then we'll look at thermal cracking and movement, which is a bit of a hot potato. During building booms, it always is, and there has been one. And then we're going to look at arches, corbels, kneelers, that kind of thing before we finish off. So, first photograph. Again, I've used this before. I like this picture. It's a job that we did in Leeds quite a long time ago. But the thing about this is it illustrates how robust buildings are, because that's had a catastrophic collapse of the external leaf, and it's caused, it was a traditional wall, but it's caused by wind pulling on the wall. A sign was on it, and that amplified that. We can see the inner leaf. But the house is still occupied. The guy could still be in his bedroom having a Zoom meeting like the rest of us. It won't, life goes on. And that's how robust houses are. But it's an example of, in effect, wall tie failure, but there are no metal ties in there. If you just look at my brand new giant, look at that. That's proper Yorkshire cursor. If we look at that, we can see the chimney flue there. We can see the floor joist that used to bear into the wall. Well, they still do, but they used to stick it in a cavity. But if we look closely, we can see these holes, just pointing them holes out. Those are where the through stones, there's a through stone still in position at that point, but these are all pulled out. I think there's one up there and there might be one up there. So it's a cavity wall, but it's made into a solid wall with the combination of the rubble and the action of the ties, okay? And the wind has pulled it over. Then we get the more common type of collapse, which is a cavity wall with rusty wall ties. And the ties have rusted and the outer leaf's fallen off. And again, it demonstrates the house hasn't fallen over. So we're not talking about buildings falling over. We're talking about really unstable walls and cracking in buildings, okay? Unstable external leaves. We're going to get onto the slenderness ratio when we talk about forces and stuff. And you can see that that outer leaf is way beyond its middle third, but we'll go into that in a minute. And then we get another type of collapse, which is very common. Again, not a structural problem for the building. It's still stood. It's still occupied, in fact, that building. What's happened there is poor lateral restraint has resulted in that lightweight apex getting pulled out. It's dragged the inner leaf with it, which is why you've got those those plastic sheeting up. And then it's peeled off or unzipped. You know, we call it unzipping. It's unzipped part of the external leaf as well. Look carefully. Let's introduce the giant cursor again. Look at the damage it's done to the handrail. That would have been a fatality if somebody had been walking up there. Okay, so they're just a little sweetener to get us going because everybody likes a dramatic image, don't they? I do. So if you look at this, there's our typical building. Load paths going from the top right to the bottom, and that's really what it's all about. Everything wants to go to the centre of the earth, and you know, unless a black hole goes past us, that's what's happening. We're all going to the centre of the earth. That's where load paths are heading. Thing to remember, very basically, masonry is strong in compression. Okay, it's very strong in compression. So you student guys, 100-foot high chimney, Fred Dibner type chimney, the bricks at the bottom are not getting squashed. All right, they're not getting squashed because they're so strong in compression. But they're very weak in tension. Masonry is very weak in tension. Okay, if you try to drag a building one side to the other, or if one part wants to just move slightly away from another part, it's going to rip, it's going to tear. That's what we mean. If loads stray from the middle third in section down a wall, then there's likely to be a bulge. Because, you know, we want it to go, we'll load the path to go down the middle, right? There's likely to be a bulge. If we ignore that bulge, then those collapses that we've seen, they're going to happen, all right? So bulges are important. And the third point, there's loads of points, but we just want the most important ones, is that the mortar is not a glue, all right? Mortar's role is not to glue all the units together, all right? That's not its purpose. Its purpose is simply to transfer those vertical loads from the top of the building down to the bottom evenly from course to course to course. Actually, that also works at an angle in an arch when we've got compression. If those bed joints are not full of that mortar, evenly full of mortar, then the forces are uneven and they can change and become eccentric. So slenderness ratio, still on the little bits of theory. I'm really sorry, but this is for my students that I know there will be some people who don't know this or need it reinforcing. Jenga's a beauty game, right? Especially if you've had a few. The thing about Jenga is it demonstrates slenderness ratio, it demonstrates load paths, it demonstrates, even when you're trying to pull a block out, it's getting sticky, it demonstrates shear, eccentric loads if you take one out at one side. It's brilliant, right? So as an example, we've got a 5 metre high wall and the outer leaf is 5 metres, say, from the DPC to the eaves. That's a slenderness ratio of 1 to 50, because it's only 100 mil thick, okay? Now, slender things fall over very easily, okay? So try standing on 1 foot like me. I'm not bad at it for a 61-year-old, but the thing is, stand on 1 foot, you're unstable, all right? Healthy ties, a cavity wall, a big, thick, solid wall is much more stable, but a cavity wall is, and the reason a cavity wall is because the ties are borrowing some of the strength from the superstructure, okay? So we can now take the thickness of the wall as the total thickness, including the cavity, even the fresh air in the middle, we can include that. So a normal cavity wall, 275 milliwatt, is about slenderness ratio of what? 1 to 18. Miles better, still quite slender. So here's the next important point. All external walls, all of them, they rely on support from the superstructure. And that's what we're talking about. That's the crux of lateral restraint, okay? We build a cavity wall out in the middle of Yorkshire Dales with no walls attached to it, just in the middle of the field. First gust of wind, it'll fall over, okay? So we'll move on now. I just made a pointer there at the bottom that if you're 6 foot tall, and you're standing with your feet a foot apart, your slenderness ratio is only 6 to 1. That's the difference. So here's a little sketch, a couple of little sketches I did on my tablet for you. The left-hand wall, typical Rubble wall there. It's got a big giant cursor hang on, here we are, yeah, big giant cursor. There's a through stone. A through stone being that stone which is longer and is turned on its end, so it spans the cavity and it bonds the two skins of masonry together. They don't both have to be stone. The outer one on the left there could be stone, the inner might be brick. It might be blooming rubble, it might be rubbish, you don't know. So we've got a through stone there, and the loads are coming down the wall, but they're generally in the centre really, because what happens is the rubble fill and the action of the through stones together make sure the wall acts as a solid wall. On the right hand side, it's not quite the same. Solid walls, they have lower ratio. Often the stones are not uniform in shape. It doesn't matter, the rubble's supporting them. But vibration and traffic can disturb all that, okay? We've got wind, we've got creation of new openings when builders knock blooming holes in the walls, for new windows and stuff like that. And the rubble, if you look at the right picture, can settle and form voids. And that does several things, okay? The load paths can become eccentric, and the slenderness ratio, because there's a big void there, gets much higher, because basically now that leaf, the outer leaf, it's not got the support. It's not got this load sharing. And so some of the stones may even tilt a little bit. And if you've got compression on one side, because it's tilted in, you've got tension on the other, so you'll get cracks, okay? So when you see, and this is the purpose of this slide, if there's a bulge in a wall, all right, especially a rubble-filled wall, but applies to bricking for other reasons, but if there's a bulge, check the cavity, check for voids. Or just assume the voids are there, they likely are, all right? So, telltale signs, now we can jump back to surveyors, and you'll find this. I'm going to try to keep you all on board with your various interests, and I know I've got some surveyors on site. Experienced surveyors know this, but we need to underline it for others. So, we're in the front bedroom of an average house here, Samuel. On the left there, on the left side, that's the inside face of the side wall of the house, the external wall. And here's a partition wall. It could be blockwork, it could be studding, it could be brick, it could be anything, it could be stone. We've got a crack running down there, all right? Got a crack running down there. And it's between the junction of the partition and the external wall. And we might have it on the ceiling as well, okay? It wasn't built like that. There are other reasons for that crack, but one reason is the outer leaf may be moving outward. And just to touch on this, when the wind is blowing, okay, you will have an alternating load, right? Negative, positive, right, on the wall. And the wall is being shaken very, very gently. And sometimes if we've not got a good firm connection, it doesn't have to be, anything massive, but if we've not got a nice connection to the superstructure, the inner leaf may move out microns or a millimetre. But the thing is, it won't go back, okay? So it's going to move out a fraction, it's going to stay there. So this is why with houses such as I look at all the time that might be 70, 80, 100 years old, that cycle's gone on a long time and it's starting to become a problem. We might get the crack at the ceiling junction here, or we might not have a crack. We might get what's called rooking, where we see the wallpaper at the junction running down here. The left there, actually, now it's reversed. This is the other side of that bulkhead. The left is the wall, the right is the inside face, the external leaf, left is partition. And we've got this rooking pattern, look, running up. Can you see? So that, our surveyor's poked his fingers in there. Naughty boy, he's poked that so he could see the crack. But when the survey's done, you just get this rooking. And we don't know whether that crack has been decorated over before. So this doesn't necessarily mean there's a big problem, but what it means is you need to look deeper. You need to check the outside, get a spirit level on it, stick a straight edge on it, and have a look, get in the loft, etc. Lift the carpet, and we can see here we've got a gap right where the wall and the floor junction. As it happens, that's pre-war, and the wall skirted board's post-war, so it's probably had a problem for a while. Something might be happening there. We can see the ends of the joist where the plaster's resting on. So, in effect, the wall is moving out. We have this one, sometimes it's obvious, massive crack. You could get your fist in the crack between the internal masonry load-bearing wall, by the way, and the left-hand side external wall. That's why I've included this window so you know where it is. You could get your fist in there, all right? Now, okay, nobody's going to miss that. We can see that the external wall's bulging out. It hasn't got any lateral restraint from that wall. There's a sloping ceiling. There might be a bit of roof spread there. We're not going to cover that today, but that might be why. There's all sorts of things happening. Now, the reason I include it is often when we're surveying cottages and old stone buildings, they'll be beautifully decorated, bijou residences, right? And you'll see a concave profile there. The wall has moved, but there's no crack because it's been filled. And the question then is, has it just been filled, or has something been done to mobilise the mass of this wall to hold that back? A repair of the bond. Loads of ways of doing that. Okay, so if you see that crack, you need to ask questions. You see that bond. I mean, if you see that curve, you need to ask questions and see what we can do about it. Because often when we hack off plaster in these old houses where there's been a hairline crack, there's a fist-sized crack behind it, full of newspaper. All right. Back to some basic structures. I mentioned about the importance of the mortar for transferring load between the masonry units from the top to the bottom and at angles sometimes. I like to think of lime mortars. It started out as cottage cheese when it was mixed, and it ends up as Parmesan cheese, right, like that. That's my grubby mate holding Parmesan before I took a bite out of it because I love it. It's disgustingly delicious. But anyway, the thing is, think of that is how soft often building materials are. Okay, so if you're going to try and resist movement, or if you're going to try and support a wall with hard things, stainless steel and things like that, then you need to consider it carefully. And what you need to consider is the structure itself. I'm bringing these quick because I'm talking too much and I know we're short of time. So these are the points I want to make. It's always the structure that fails first. It's never the fixing or the tie. Because you've got a hard thing pulling through a soft thing. You cut cheese with a cheese wire, and to some extent, remedial wall ties, helibars, various things. If you overload them, they will just cut through the bed joint. They won't hold the wall up. All right. Got some samples of ties there, and I'm going to now cover the principles of fixing technology. Very basic. On the left-hand side, we've got these. We've got helical ties. Lots of those around. You can resin bond them in. You can screw them into timber. You can friction fix them. And on the right-hand side, we've got there the mechanicals. These are mechanical expanding ties, expanding to grip the hole. And there we've got a resin bonded tie. Actually, there, wave that at you. See, look at that. It's great that. Because we've broken that open to show how they work. Because you fill the hole with resin and then you put your tie in, and basically that holds it all together. And from the point of view of bearing stresses, what you want is you want to spread the load. You don't want point loads in those weak materials. So here we have these inflated sock anchors. And the thing with inflated sock anchors is it's a bit of a misleading thing because people will think, oh, big, chunky, massive, strong anchors. And they are. I mean, sometimes we put them in concrete structures and test them to, 40, 50 kilonewtons. It's ridiculous. That's in civil engineering. But in Joe Bloggs' semi or cottage, when you're installing something as strong as this, you're installing it to be gentle, right? Not to be gentle on the structure, because by having a bigger diameter hole and a deeper hole, you reduce the stress imposed on the substrate when tension or compression is applied. All right, I'll just briefly show how that works. So there we've got a tie on the inner leaf. This is the inner leaf section. And this is the cavity. On the left-hand side is the cavity. On the right side, I haven't put the plaster and the guy smoking his pipe, but on the left-hand side, you've got the cavity. And that tie goes out through into the outer leaf. And if we pull on that, if we put a tension on that, like for example, if it was a windy day, it would be pulled. The resin around that is in intimate contact with the sides of the hole, and it's sort of fixing partly through adhesive action. But polyester resins, for instance, are not an adhesive, and that's what I use a lot of. But mainly because the hole is not smooth, it's sort of got lots of indentations in it, and where the resin's in intimate contact with those indentations, we get a keying action. Okay, so it's holding mechanically. That creates a cone of resistance, all right, within the wall, and it shares the load over that big area. Okay, and that's one of the good things I like about grouted anchors, because the entire internal surface area of that cylinder, if you like, that hole, is being mobilized in transfer of the load. Okay, if we look at, say, a mechanical tie, nothing wrong with mechanical ties, I'll get onto that. There's no such thing as a best tie, they all have their purpose. The contact patch is smaller because you've just got this little, you've got that little end there, which works a treat, don't get me wrong, but naturally it will impose more stress over a smaller area, but it still mobilizes a nice big cone. And notice that cone passes through the bed joints because the bed joints are there to transfer load, as I mentioned earlier. So again, that's another way of holding it. That's how they work. Now then, when we apply a tensile load to that, to test it, we are replicating the wind loading, the negative wind loading. Okay, if it is negative, it can be positive sometimes. It's not the same for the outer leaf, because the outer leaf tie, if we take it, and this is the outer leaf, we've got alternating wind load here. So it's, you know, push, pull, and that's the thing about the wind, you know, we've got eddies and rotoring and stuff like that. But by and large, the dangerous one, I mean, let's face it, the wall's buttressed by the house. So what we're really worried about is the tensile forces pulling the wall over. So the cone's reversed. It's the wall which is being sucked away, and it's the tie which is fastened in the inner leaf, which is resisting that load. You know, it's Newton, every action, there's an equal and opposite reaction, isn't there? So the cone's reversed. So you have to consider that, because when we drill holes through walls, we will often spall a chunk off the back. BRE studies have shown you can take, you know, up to a third or even a half, depending how you do it. And that will reduce the amount of material within that cone. Okay, the diameter is not a problem, and look, a lot of it's missing it anyway, with it, depending where that fixing is. I'm going too far here, I'm going to have to move on. But anyway, so tension tests in the outer leaf don't actually replicate tensile loads on the outer leaf fixing, all right, for that reason. They're still absolutely valuable because they check the workmanship, so you should always test them. All right. How can we reduce that spalling? Well, you could drill a smaller diameter pilot hole. Good thing about these little things, these helical ties, is they can be friction fixed. You don't get a lot of expansive force, but the good thing is you can use a smaller diameter pilot hole. It reduces the amount of spalling. All right. Or in saying that, the contact patch is very small, so that increases the amount of transfer at point where it's in contact. So there's always two or three things to think of. Use low percussion, diamond drill it, drill in the bed joint, that reduces spalling, and consider the tie method and the method of installation carefully. None of these is right, wrong, or indifferent. They just all need to be considered. All right. Staying on the point of this, bearing stresses, this is just a guide. What another way around reducing bearing stresses is put more ties in. If you put more ties in, okay, so increase the tie density, as we say in the trade, what that does is it decreases the amount of work each wall tie is going to have to do. So if you've got a soft external wall, rubbly filled, why not tie it at double density? We always tie bulges, if it's already moved, wider cavity at double density, okay? So you ask your structural engineer, he might let you lower your tension testing regime because he knows the ties are doing less work, all right? Less stress on the substrate. You're not going to stress the substrate. That's what this photograph is showing. That's a piece of A4 paper, you know, like that. And I'm pulling one side and my wife's just nipped the corner and nipped the edge. And when I've pulled it, it's torn. Now, on the next slide, you'll see an example of high density stopping that. So less stress on the substrate, better redundancy. If one or two of the ties have hit an open perp, it's not as important if you put twice as many in, is it? So better redundancy if you increase density. So I'm talking now not about, say, the council house job is 600 houses to do, and the guy who wins the job is the guy who's the cheapest. End of story. You know, that's what's going to happen there. But when you're dealing with the gable of a single house with a huge bulge in it that needs to be held in position, that's when you're going to be able to put a lot more. You just put more ties in. So increasing density has some disadvantages. There you can see the other example. Julie's holding the paper with all the fingers, and I can pull as much as I can. I can't get it because I'd have to tear the entire piece in half. In other words, I'd have to apply a lot of additional load to tear it. I hope I'm not going on too much about that. That's the important thing about reducing bearing stresses. Trouble is, if you put more ties in, it costs more money. The vibration itself might be a problem. If you're going to drill a load of holes in a wall that's already a little bit unsound, that's a problem. You've got to think about that. You might have to use diamond core drilling, which we do often. Also, if you put loads of ties in, especially in a more modern building, you're going to reduce the vertical and horizontal flexibility, which is key. Because, you know, we've got movement joints in the outer leaf and various other things, and we recognise the outer leaf moves in relation to the thermally stable inner leaf. As we insulate the houses, the interior will get more stable and the exterior will get less stable thermally, right? So you're bound to get differential movement, so don't over tie it. Now then, back to surveying. So I know we're up and down all over the place, but it's important because we've got a lot to cover. So look at that house, post-war, 70s, 80s. Apex is bulging out a little bit. Go inside. This is after it was stripped off, but basically we've got these cracks running around the front and rear walls. They're not on the side walls. They come through. That was one on the survey, so you can see the crackers come through the paper. Right? It was missing any holding down straps. There weren't any. Right, so they've had to put new ones in a bit longer than before, and a lot more of them to spread the load. Again, bearing stresses. It's better to use a lot of fixings doing very little and try and rely on, you know, things being very strong. And that's the misnomer I mentioned about with the big Syntec and sock fix type anchors. You think, oh, they're big because they need to be. They're big to increase the surface contact area, which decreases the bearing stresses. All right? And that's just a sketch off the job. You can tell it with me who surveyed it, because I don't use CAD, so I've done that on my little tablet. But in effect, we've put the straps in, we've put some diagonal braces in that were missing across the rafters, the truss rafters. We've put straps across them, and we've tied it all securely into the gable. Loads of ways of doing it. So post-war instability, again, post-war house here, on a hill, slight outward movement of the apex gable up there, and a little bit of horizontal cracking and slight undulation. So naturally and quite rightly, the surveyor said, I think we've got a wall-tie corrosion problem. But it's not that simple. This goes hand in glove with wall-tie corrosion, really. It did have wall-tie corrosion, because when we check them, you can see there the rusty tie. But the main reason for the bulge is that the inner leaf has moved out. It's a lack of lateral restraint. Okay. And if we just, rather than try to, to photograph a blooming spirit level in the roof, just to demonstrate that that rafter is straight and true, all right, and so is that one. And when we've checked it, at the bottom, the gap between the blockwork is about 60 mil, and it's over 80 mil there, okay? So and that's at the top, all right, that's at the top. So it's moved out. So why? Well, low weight, these are low density blocks. Weight gives support, okay? Again, for the students, if you were playing Jenga and I pushed down hard on the Jenga, it won't fall over, it won't be slender anymore almost, right? It would, but let's not get too deep into science. But the point is, weight gives stability. So here we've got no weight, right? That's the first thing. We've got no straps. There's no blooming straps on the roof, so it's got no lateral support. It's an exposed position on a hill. There's gables opposite, which mean the wind funnels through, and the ties are corroded. So double whammy. So for surveyors again, I like this little example. It's the middle house we're looking at, okay? Okay, gable, another gable. Two gables close together. That increases wind loading, and it's also the alternating nature of it, because when wind, I used to fly paragliders, and you always avoid going behind the ridge of a hill, because when you go behind the ridge, you can get into a rotor, and your paraglider turns into a bag of washing, right? And that's because when wind is put under pressure, as soon as that pressure is released, it goes mad, right? And that's what happens. Wind is blowing through the gap, that's sucking the both walls together, but as it escapes, it goes into rotor, and you get this, vibration pulling the house. So that's the first sign. The second is the door is very tall, the window is very deep. So we've only got a tiny bit of masonry on the return. And of course, it's that lovely bond at corners that gives restraint. All right, it gives vertical restraint, horizontal restraint. If you start taking bits out like there, it reduces it. So you're on notice there, aren't you? And walk around the side to look at the gable. It's used good bricks at the front, bad at the back. So we've got a poor bond there anyway. And point is dropping out because the walls are moving differentially. Okay. In addition, and what went wrong, okay, so we've got the wind loading. We've got no corner restraint. The back corner hasn't moved, but the front has. The floor joists run parallel to the gable. So when you're in there, there's a staircase as well running up the gable, which means the joists have been trimmed around it. So there's no restraint at that point either. And we've got all those telltale cracks I showed you earlier at junctions and things. Okay. No straps, of course, so it's easy. So it's had a full monty of interventions, various bow ties, helifixes, God knows what's gone into it. So if we look at this pre-war semi, common, everybody knows an house like this. Again, because of the width of this door, we've got a reduction there. We've got a blooming carport there that acts like a sail. It's getting lifted and pushed and lifted and pushed. And the wall, remember, we've got, because the staircase runs up it, it's the central bit where this is fixed. That hasn't got the lateral restraint afforded by the superstructure because the joists aren't resting in it. And that's why we've got a little bit of crack in there. We've got a bulging wall. We've got cracks at the junctions. This is the top of the landing. So that's needed lots of intervention. We've even had to heli-beam the central section to stiffen it across that void where the staircase is. And those little dots are just where the surveyors picked out for visual purposes where the lateral restraints are going. You notice he's omitted the bathroom because the client said, no way are you putting any stuff in there. It's a brand new bathroom. Right? So that's another reason why the heli beam has been returned around both corners. Just some points there about that, which I forgot, but I mentioned. So move on. So I mentioned heli-fixed bow ties, but that was just, you know, because that's what we use on that job. Ordinary straps done properly can work very well. Not plugged and screwed into the wall because plastic creeps under load, and you should never load a plastic plug and screw fixing coaxially. It should only ever carry really, you know, sort of shear loads. But it's always, you know, the manufacturer will say, oh yeah, I use these all the time. But, you know, there's an example, look, in the floor void, you've got to miss all the pipes and wires, and sometimes strapping is more appropriate. And if you're in a loft and it's all accessible, you know, you can use those. The main thing is to make sure they are fixed to the external leaf in remedial terms. On a new house, they're hooked in the cavity. On an old building, that fixing, or those fixings you put in the upstand of your strap, you know, in this thing, yeah, and you put in that, yeah, they need to be as near to there as possible to reduce bending, but also they need to be resin bonded or grouted or mechanically fixed in somewhere to the outer leaf. I don't like mechanical fixings though into masonry. Here's a little thing, bit of crack stitching. That wall's cracked up, badly cracked. So what we've done is we've restored its lost continuity because we don't want the wall to re-crack when it's all plastered by putting some crack stitching in. But we've also extended that into the outer leaf. And if it were brick, it would have merely been resin bonded in the outer leaf to act as a lateral restraint, because this close-up shows you there's quite a big gap between that wall and the external wall, which is the left one. So what we've done is that bar actually has been passed down a big diameter hole into the outer leaf, and then a sock anchor, something similar to this. I know it's got a piece of rubble through it where it bonded that, is inflated afterwards, so it grips it. So that's just that. If you notice that crack, actually, it runs the wrong way. You'd expect it to run this way if this cracking was due to lack of lateral restraint. Actually, there were no lateral restraint, so we haven't got any resistance from this wall, so there's no cracks caused by that. These cracks are caused because the builder knocked an hole in the wall below at ground floor level. Didn't support it right. That's what happens. We can also put long sock anchors like this, several meters long from the outside and into the body of an internal wall. But again, we're not going to get into too much about remedials on this. So, check my timing. Oh, I've got a bit more. Slow down. Sorry about that. So, why not just point the cracks up if we get cracks in a building? Okay, so I'm going to tell you a little story to illustrate. So what we've got here is a newish property. And these bricks at this point, they were cracked right through, and the cracks actually went just straight down to the here, which is quite natural because you can't see it, but there's a gable to your left, which is, so there's a lot of load, a lot of compressive loads going down that pier. Not a lot of weight there, and it's quite a slender panel, so it's weak in tension anyway, and it's torn between the two, okay, and it basically cracks all the way down. So the builder basically replaced the bricks that had cracked and didn't do any crack stitching or anything else. And of course, it's not resolved the issue because the movement joints were defective. And even if there were no movement joints, it's not resolved the issue because the wall has no longer got the continuity we want, that homogeneous panel that we want. So any movement, however slight, will favour the original crack position, and it's just cracked around. I've covered them with yellow to mark them, you wouldn't have seen them, but it's just cracked right around the repair. All right. So he replaced the bricks. It didn't add any strength, and the new cracks just followed the old one. Some tensile support with some LE bars or similar other flavours available would have been sensible there, as well as sorting movement joints out. Now then, get a copy of BRE 361 because it's a good document. I recommend you all download it. So I don't think they'll sue me for using a bit of it. I think you're allowed to if it's for teaching. So there you are on the left-hand side, thermal movements, but differential materials. So you get cracks in certain bodies of the wall. this is what I like to think of as unsightly nuisance cracks, not structural problems. If you leave them alone, the right figure 3, as it's labelled in the book, shows you what can happen, because you get a hairline crack as it relaxes. You know, you've put your face pack on, or your daughter's made you have a face pack, and she's laughing at you because it's purple, and as the water dries, it shrinks, pulling your wrinkles out, hopefully. But obviously it shrinks and then it cracks, doesn't it? Because it's made out of clay, which is what, you know, walls are made out of generally. It's powdered stuff made into masonry units and mortar. And it cracks. It cracks minutely. But if the cycle's repeated, which it is with the sun and the signs, you know, highly insulated houses, basic sunlight, then a frosty evening, then the cycle starts again and the crack wants to happen again. But it's never closed because grit dropped in it. And that's the point of ratcheting. So we need to move on because get the document. Anyway, so here's an example of that. Mixture of materials. The block work, the render's quite expensive, so we use cheap blocks. We don't put them on bricks. And there are cracks under every single narrow, slender panel, all right? For exactly the reason outlined in that, all right? There is a movement joint behind this pipe. There is a movement joint behind that pipe, but they have been put in to accommodate the clay shrinkage of the clay brickwork, and the shrinkage of and expansion of the blockwork is much greater. So we've got cracking. Talking about movement joints, get yourself a copy of NHBC Guidance 6.1, which is brilliant. And it tells you don't put joints through windows. The windows, the lintels, and everything else resist, you know, the functioning of the joint. So it's pretty obvious, but you'd be surprised. If that's the right way, straight from DPC to eaves. Now and again, it has to go via a window, and it's a skilled job, but you can put slip planes in there for that. However, if you notice, these do show, just nip back to the last one, some dashed lines. That's suggested bed joint reinforcement, particularly important if you've got wide windows so that the panels below have a ratio height to width of more than 3:1. Well, yeah, whichever. If they're wide and not tall, they'll tear very easily because they've got low resistance to tensile forces. So, quick example. The builder's put his joint in already, which goes from the underside of that sill down to the head of the door. It's been condemned by the insurers. We've come along and we've put a slip plane around it. Now, even though we put a slip plane around it, even if it was a perfect joint, we would also put bed joint reinforcement along there, because this is a slender panel. It's what's known as an at-risk panel, okay? Because it's low height. It's weak, even weaker than weak in tension, okay? So we put some bed joint in there. But because we know that this joint is actually, it's doing something, but it's never going to be perfect. And the reason for that is A, it's a slip joint, and B, it's got a blooming porch bolted to either side. Right. So as a result, we've put helibars in these as well. All right. Another example here. This is again expansive corrosion, and we've got so not expansive corrosion. I'm talking rubbish. I looked at my watch then. We've got thermal cracking, and it's very hard bed joint material, which was not helped, and that's the wall, and it's cracked there. Okay, it's cracked down there. Now, there is also a crack here, and that's just to point out that these cracks, thermal cracks, will often open at the weakest point in tension, but they will also often open at the point of restraint. And what I mean by that is there's a higher loading on the gable, but also it's well bonded. If we use the yellow gable, you know, it's a corner. It's got that lovely cat's cradle bond. So it's very inflexible vertically and horizontally, whereas this is a panel that's expanding and contracting, so it's cracked at the point of restraint. So that's another little tip for you. And of course, we get defects in movement joints. New ones that have been done badly by the brickies who were in a hurry, so that's plasterboard that they've used as a packer inside it. That's bed joint reinforcement, not reinforcement, it's a mesh, expanded metal that's been placed actually across that one. The boroscope that you're looking through there is in that hole looking up, and you can see the blockwork either side, and somebody's put expanded metal across it. Idiot, really, but there you are. So retrofit movement joints, in other words, joints put in after construction, either because they were missed or because the existing ones were compromised, is a specialist job. You give it to the builder, especially if he's dropped the ball and he's been beaten up and say, you're not getting paid, get it done, then this happens, all right? This sort of thing. And there's another one. We've got the marks on the wall where the ties are being put. We've even got the pointed horizontal lines where you'd expect the slip ties to be. Very untidy looking thing. That's a close-up of one of the slip ties. These are ties that go across the joint, but they're designed to allow the joint to open and close. That's important, you know. It's pointed them in, so that's, you know, no good. And when we've exposed it, you see the helical shape of the thing there, it's completely bonded in mortar, so that's rubbish. That's a new build slip tie. The reason I've included that for you is because often, well, not often, but periodically, brickies will just remove the sleeve and throw it away because they're in a hurry, or they'll install it incorrectly, either bonding part of this across the cavity, I've seen that, or pushing this sleeve on firmly so that the metal tie, the other side here of this, is right to the back, in which case the joint can't close. So retrofit movement joint should look like that. That's a correctly installed slip tie before it's pointed away. I like to see the little tube sticking out, to be honest. And the ties need testing. Just a quick example, when we get from thermal nuisance cracks, you know, which are unsightly and cause, you know, owners to have sleepless nights, we get to real thermal movement, which causes damage. All right. And so here the coins, which are very smooth, they don't have frogs and things. Often the perps are half empty as well, so you get eccentric loading, you know, where they're touching the wall. They get shunted out of position by ratcheting, which gradually goes on. And we've seen some of these. That overhang there, remember that 3 stories up, that overhang is about 40 mil, but I've seen them with greater overhang than that. All right, so that's when ignore thermal movement at your peril. It can really come back and bite you. Now then, here's an arch. I love arches. Arches are amazing. They're incredibly robust, right? They very, very rarely fail. This one hasn't failed even, but the abutment has failed because several reasons, okay? The left abutment's too narrow. It's not resisting the thrust here. This wall at the other side goes on forever, all right? It goes on right over the other side, so brilliant. So it's not resisting, so it's moved out slightly and it's getting pushed over. We've got this big timber buttress holding it up. The upper abutment is quite low. You'll see we can divide the abutment into 2. The top part is important. If you see a flying buttress coming out of the side of, you know, some massive cathedral or whatever, there'll usually be a pinnacle on the post supporting that. And that's to drive down that load so that it doesn't pass out of the pier and it goes straight to the earth. So you need a lot of weight there, okay? And there isn't, you know, it's because the arch is tall. The arch is coping well because it's a segmented arch, you know, with the nice sort of tapered stones. But this would have fallen over if they didn't buttress it. The arch is shallow. That means more thrust. The shallower the arch, the more thrust there is. You know that if you played that, tried to build the cards. Impact damage is common in barns, right? Not just the tractors, but big animals and things. Heavy doors flapping about in the wind. They're putting loads of stress into the jorms and, of course, lack of maintenance. Builders... farmers, they're busy, they work like dogs. It's a thankless task being a farmer, but they haven't got time for maintenance. So, like I say, arch is very robust. We've got typical arch failure. The window frame's holding that up at the moment. And I just want you to just look carefully. You'll see the typical pyramid cracking, right? So, in other words, the load pass made its way this way and that way, not via the arch anymore. And the brickwork is now corbelled. This brickwork is now corbelled over and resting on itself at the centre at the top. And this is just nothing. Look carefully and we'll see these cracks running in the rings. That's the shear stresses generated by arch failure. All right, well, it's been generated in all arches. But if we just hold our hands like that and then imagine if we want to make that shallower or deeper, your hands have to slide. All right, they have to slide up and down. Masonry don't do that, it rips. Okay, so in a basic way, that's the effect of shear cracking. You might call somebody in to do a bit of crack stitching. That's disgusting. If you look, my brick tile logo is upside down on this slide, and that for good reason, right? It's the roughest job I've seen in ages, but we do see a hell of a lot of rough crack stitching. Not only is it rough, it's not doing the repair. The ring's still cracked. All these cracks here, it's lost continuity. Somebody's just cut that with an angle grinder and driven it in. It's appalling. It damages the whole reputation of the methods. A specialist will never do that. That's been done by the conservation specialist who did the line pointing, by the way. Should be ashamed, but anyway. Right, so arch failures. I just want to underline the abutment thing. Here is a job I looked at a few weeks ago. It's got a very shallow arch, and look there, there's brickwork above it. And that's the very shallow arch. There's 3 of them, not a crack in it. I went back last week. Amazing that we're going to do this talk, really. And they've taken the masonry off. They've taken the load off there and the load off there. The cracks don't show up on the photograph from this distance, but they're severe. And this is all now in tension. It's not in compression like an arch should be. It's got tension cracks in it, and it could drop out. We've had to fence it off. And it's happened because there's more thrust there. There's a very narrow abutment here, but it was coping well because it had the weight above it, holding down, driving down that load path to the earth, to the center of the earth, right? And when they've taken the weight off, it's become a danger to everybody visiting that site. Loads can be done. Loads of specialist things can be done to fix it, but that's for another talk. We're nearly there. Right, so copings and corbels. A corbel and a kneeler leans out from the building, obviously, and the maximum, again, this is from NHBC guidance, is 1/3 of it should protrude. So many times you'll go on these jobs, particularly post-war building booms like, back in the noughties and previous ones, 50% of that kneeler protrudes, but that's been added to by the weight of this and the thrust of the badly installed corbels. So watch out for these. This is from a job where the whole row on the verge slid off, right, like a train going off a bridge on, and crushed the porch. Okay, so be careful. You can get complex mixed defects. If you look at these pictures, this is this building here, which has got these very long. It's got the movement joints are rubbish. It's got very long stretches of brickwork. It's got intimate contact. If you look where my cursor is now, that's the concrete frame of the inner structure. And that column in between all the windows is resting on it. This cladding is thermally active, so we've got cracks between the two. What I said earlier, the point of resistance. We've got very hard mortar binding, which is terrible because it's not allowing the cladding to sort of, shuffle around as it warms up and cools down without causing a lot of cracking. It can't move. It's held hard by that mortar, so it just cracks. Severe wall tie corrosion as well, combined with low wall tie density. In fact, I used this as an example in my January webinar on this, and showed you some ties in it. So we're at the end now, folks. I'm sure Andy's going mad. Just wanted to show you this. Neil Crozier sent me this because I was chatting to him the other day about this presentation. And if we look at the face of this bistro next to a river, we can see big chunky patras plates have been put in. That tells us that at some point they thought they were needed. Maybe the wall started to bulge. We've got some openings have been formed. Never a good idea with rubble walls without a very skilled builder. That's it after the collapse. And you can see the collapse is nothing to do with lateral restraint. Absolutely nothing to do with lateral restraint. It's been undermined. We must stress this for you, boys. Everybody, boys and girls, you all must remember this. If I've implied it's simple, the basics are, but it's not a simple thing. You need a specialist. Wall tie installation, retrofit, lateral restraint arch repairs require a specialist. The little animations that all these companies do, showing how easy it is, are responsible for terrible work, right? If defects are not straightforward as well, i.e. that bistro, a specialist should recognise that and he'll call in a structural engineer. The structural engineer is crucial, is your friend, right? And his independence is important, which is why I don't employ a structural engineer. Because if I need structural engineering advice, I need it to be independent, okay? All such repairs that you've seen here can be undone by poor workmanship and regularly are, okay? It's hidden, like the new build even with the movement joints. It's hidden, nobody can see it, don't matter, right? You need people who are engaged, right? Who are going to do a good job. So thank you very much. Here's some further reading. These books are great. Also, the Construction Fixings Association website is a treasure trove, and BRE DG361. Thank you very much.
No, well, thank you, Brian. Thank you. And I wasn't going mad.
Well, I thought, blooming heck, I'm going to have to go here to fit all this in. Have I done it too quick?
You did. I have to say, you did incredibly well. And folks, I mean, there was a lot that I have to say, and Brian and I were talking beforehand, there was a lot that we wanted to get in, but we've only ever got a short window of time in the morning, and it's possibly something that we can follow up on if you guys are interested in finding out more. But if I take us on to questions, because we do have quite a few questions, and folks, if you do have a question that you've maybe not posed via email or via the chat, then I suppose now is your chance to kind of pose that question. Just feel free, just use the comment facility. You can either see it in the right hand side, or if you are watching the recording of this, just simply email me at andy@property-care.org. Please make sure you tell me the webinar in reference and pose your question, and I will endeavour to try and get that answered for you. So starting off with questions for you, Brian. First question I've got is from Gemma. She's asking, have you got any recommendations for cavity wall ties for bathstone outer leaf and concrete blocks as the inner leaf for an extension?
Oh, you mean for new build?
She has it specifically said for new build. She's just referencing the outer leaf being bathstone and the inner leaf being concrete blocks. Do you have recommendations for concrete blocks?
I can't survey online. That's the first thing. But the main thing, the concrete blocks, if they're solid, then there's a very wide variety of fixings that'll do that. If the material is bathstone particularly soft, I don't know. I'm assuming it must be. What you're looking at there is you want to make sure that the tie that you use isn't going to overstress the material. And there are lots of ties that will work in very soft and friable materials. You either have a smaller diameter tie, because if you're going to install them from outside, it's nice to hide it. And it could be friction fixed, it could be resin fixed. I wouldn't use mechanically expanding ties in that situation. You could use them in concrete. The thing to remember with inner leaves as well is modern buildings, if it's an extension, there'll be insulation in the cavity. So you don't want to drill too big a hole that's going to spoil the inner leaf and damage the insulation. Often in those circumstances, we actually would tend to favour something like a retro tie, which is where you use one of these and you drill a very small pilot hole in the inner leaf, drive it in, test it, and then grout it into the outer leaf and fill the hole. And you could put those at the bottom of the perps and they'll virtually disappear. I hope that answers your question.
Yeah, I think the one thing I will emphasise, folks, for all those that are listening, there is a lot of questions that, to a certain degree, are slightly difficult to answer without physically doing an investigation. So if you can, it's maybe a little bit finger in the air. Brian will do his best to answer it. But this next question is the prime example of that as well. It's maybe a little bit finger in the air. But Human is asking, what is the rough ratio for wall tie proportions when putting them in against timber frame structures and brick wall cladding? And again, I think that's one of these ones where finger in the air investigation. But is there any sort of guidance you can give, Brian?
Well, the thing is, at the end of the day, there are guidance notes on this. But with a timber frame, and this is a remedial perspective, not brand new, the ties must go into the studs, not just into the sheathing. I have done one job where specifically they were put in the sheathing, but you need a very high density for that because the ties won't be able to do much work individually. You might only get 500 newtons on a tension test on that. And that can slightly defeat the object sometimes, depending on the design, because timber frame and cladding move relative to each other in all planes. So you don't really want something too rigid or too many things crossing the cavity. So it's a balance. I mean, it's the wind loadings dominate. So if you've got a strong frame, then there's no reason why you need to go beyond 2.5 ties per square metre, and as long as the cavity is not too wide. If the cavity is wider, then you'll have to increase the density, perhaps, 3.5 ties per square metre or even 5 ties per square metre, which is 450 by 450. But bear in mind, usually you don't get that domino pattern so much on timber frames because the ties are just installed in vertical rows down the studs. I did see a job the other day actually where somebody had put a row of ties in the last stud in the corners. So literally there's a wall tie within 200 mil of the corners. Never ever do that. You don't want to tie within 500 mil of a corner. I hope that is...
Well, Andrew Bourne's actually just thrown something interesting. It's an interesting spin because we've spoken a lot about cracks and etc. But he's asking, do all cracks need repairing? Can some just simply can you just apply a monitoring program?
Of course you can, yeah. If there's a crack in a wall, then generally speaking, Okay, well, why is it cracked? That's the first thing. So let's assume in this case, we know it's just nothing. It's just a small little bit of settlement, a tiny bit of thermal movement, and there's a crack. There's nothing to stop you just monitoring it. In fact, there's nothing to stop you raking it out and pointing it up and doing nothing as long as you can monitor it, you know. Really, the reason for crack stitching is often that damage has been caused that shouldn't have been, and there's a claim, or there's somebody not happy, okay? Or the property is being sold and a buyer needs assurance it's not going to re-crack, okay? So introducing that tensile strength, that little bit of tensile strength will just strengthen that area. But if there's an underlying reason why the walls are being pulled to and fro or settling up and down, I defer to structural engineers at anything below DPC level, you know. But basically, if that sort of thing's happening, then all you're going to do is shift it to another area, you know. So it's important that you get advice, that somebody looks at it and says, yeah, I'm happy, let's repoint it and look at it next year. Or, yeah, I can see that's just a thermal crack. Oh, it's going to, I don't want it coming back, so I'm going to crack stitch it. You know, there's a lot to it, you know, and this is why really it is a specialist job. Structural engineers are king. Remember that. We defer to them all the time.
Okay. Well, here I've got this next question is actually one that's just come in via email, come in from Jane Preston. She's asking, are there any common errors which surveyors mistakenly not take into account wall tar failure when they're doing a visual inspection? Are there any common things that you come across that surveyors maybe just don't pick up on? Yeah,
probably the biggest issue now, which wasn't such a problem probably 20 years ago, is surveyors still have a habit of looking at a cavity wall, and if there's no horizontal cracking, they think there's no wall tie problem.
Right.
And that was true probably 30 years ago. Because the post-war poorly galvanized wall ties, wire ties often, small section, have not yet begun to rust severely. They are now rusting severely, but they don't cause horizontal cracking, right? So horizontal cracking is a reliable sign that there's a severe wall tie corrosion, provided there are chunky fishtail ties in. But it's no guide whatsoever when it's, say, a post-war property that's got wire ties in. You can't tell. Until you look at them, you can't tell whether they're there or whether there's basically just a rusty stain where they used to be in the outer lathe, which we do find. So that's the biggest one. Other ones, yeah, usually if you've got severe corrosion, which has caused a lot of horizontal cracking, there are consequences. And those consequences, your wall is weakened generally. And so this is why we're finding a lot of the time lateral restraint issues go hand in hand with wall tie corrosion. Because you and I, we all know that you look at houses and they're identical, but one's got a problem and one hasn't. And it's because over the decades, something might have, an extension might have been built, there might have been a bit of vibration through some reason, and that's been the trigger to allow the wall to move a bit. And now, whenever there's a storm, it moves a bit more, you know? So wall tie corrosion is similar. In fact, God forbid, I hope I don't get sued for this, but I even should think that the fact that we've drilled so many inner leaves may have been the trigger for lateral restraint to manifest. Because the house was built with no lateral restraint at all, and many are, and they're healthy to this day, they're perfect, but some are not. And sometimes it might have been, there's been a trauma, and wall tie corrosion causing a lot of cracks, other things, that's the trauma that's maybe now allowed it to start going. Okay? So look out for that.
No, well, just on the kind of like a question that's actually just come in, but almost kind of sounds off what you've been discussing. But Alex was asking, is there a rule of thumb as to when a structural engineer should get involved?
Right. Okay. Yeah. Well, roughly speaking, if we see any cracks which go through the damp course or go down to the ground, we recommend a structural engineer. If we are certain what's causing the crack, in other words, we've looked at it, we're experienced, and we are certain that the lintels failed, and we've got that lovely typical pyramid crack over the window, we don't call it structural engineering. But if we've got something that hints, for instance, at more than a problem, like you might get widening cracks as they go up, eccentric loadings, bulges that are severe, you know, if we're on the borderline, we're well past the middle third, you know, you need structural engineers' advice. And actually, in our written reports, because we're a contractor, we have to be conscious of the fact that we're biased. We might not think we are, but we are. It's inevitable. We're humans. So I always recommend to our clients that they get an independent structural engineer. And we even say to them, although we're going to guarantee this work, you can have it independently supervised by a structural engineer. Why don't we get one involved? It's never a bad idea to call in a structural engineer, okay? It's a few £100 or something, but it'll give you the peace of mind, you know? So, and contractors vary, and I don't know everything. I'm doing my best. And it's the same for these other guys. I know there's some of my peer group on the thing. We're all doing our best. It's always nice to talk to an independent structural engineer, in my opinion.
Yeah, folks, I'm just want to say that there's been a whole chunk of questions that have come in. I am going to try and kind of group these questions together as best I can, but I don't think we're going to be able to answer them all. But what I will do is I'll pass them over to Brian. I'm not going to give him any. I'm not going to say any promises, but he may get back to you, he may not. But if not, we might be putting a wee web page together with maybe some answers. But Brian, if I could just ask, if you just with time being short, if you can be as short as possible, maybe with some of these answers. And I know it's difficult, but I do have a question that I did promise I would ask. It comes from Patrick Harvey-Blake. Now, he's not giving me context to this, but I am assuming he's coming across a building here where he's suspecting movement, and he's asking if there was no signs of lateral restraint straps, but no signs of suggested movement in the structure, would you still be recommending further investigation? Now, he's put in as well, additional, I'm a wee bit unsure what he's meaning here, but he's put in this example, consider purlins are built into the external leaf. I'm not a techie, guys. Maybe that's something you get. Where...
Yeah. Right. Well, yeah. I know Patrick, as it happens, is a surveyor, and this is a problem for surveyors because now it's a litigious situation they're all in. They've got to find everything. To me, my own opinion is if there's no evidence of movement, no cracking, I'm not really going to start checking for straps and things that are there. I would in a new building because obviously they're lighter. You know, you've got lightweight products and things. But if you've got an old semi that's been there for 90 years or 70 years, and it's got no straps in the roof, and it's got joists run parallel to the wall, and the staircase runs up the gable, but there's absolutely no sign of movement, not a problem. But if there are signs of movement, that's different. And as I say, that might be the only house on the road. It's been unlucky. The others are nicely planted. But it's one for your insurers, maybe. That's the trouble. I feel sorry for my Ricks mates, honestly, because the way it goes nowadays, every home buyer just blames them for everything, no matter what.
Well, next question I have, and by the way, big thanks to those that were offering suggestions on this in the chat. But there was chat asking about, was there any recommendations towards boroscopes and metal detectors for locating steel wall ties? Do you have any recommendations?
Well, I've always used the white ones from Scotland, but they've gone into liquidation. We had to buy 20 before they shut the door. So I'm afraid on metal detectors, we're all in the same boat. I'm sure some of my peer group, AD and Ross and Russell and the rest of them, I'm sure they might know. So I'll ask around for you and maybe see if we can. But metal detectors, I'm not sure. Boroscopes, we used optical boroscopes for years and they're great, but now they've been made redundant by digital boroscopes. Digital boroscopes are cheap as chips. South Survey and these people, various companies online sell them. They're not very robust, but they do the job. So yeah, just use a digital boroscope.
All right. Well, I'm coming to the last of the questions. I think I've got enough time to pose. I'm actually kind of grouping a question here, both from Aziz and Patrick Harvey. It's to do with movement joints. Should retrofitted movement joints always be fitted to internal leafs as well?
No. If you read the guidance, long stretches of internal walls should have movement joints. I have installed one for ages, and I've not seen a negative result of not doing. I'm talking about normal residential properties here, right? all of the actions taking place in the outer leaf if it's thermal movement, because the outer leaf, it's insulated from the heat of the inner leaf nowadays, you know. So really it can be below freezing to 40 degrees, because masonry does get very hot when the sun's on it, within a 24-hour cycle. So it's usually just the outer leaf which is active, thermally active. The inner leaf's quite stable. That's why we use these slip ties and things, because if you imagine it, when you cut a slit up a building, you weaken the outer leaf massively when you cut up that outer leaf. So the ties restore some of that strength. But if you put too many in, they'll impede the action of the joint. So slip ties are able to provide some of that flexural sharing between the walls either side, so it don't weaken it too much, and it still acts as one wall, without impeding that differential movement between the two skins. You'd be amazed how many times the slip ties are just seized in the holes or missing, or see some shocking things. But anyway, we put those right. That keeps us in business, so good.
Well, I'm interested in hearing your opinion and just sticking with movement joints, because it came from this came from Aziz as well, where he mentioned that where introducing movement joints were not required weakens the structural panel, especially close to corners and returns. Now, he has mentioned that NHBC have clear guidance on this and minimum dimensions of movement joint location. I mean, do you have any opinion on this?
Well, the thing with movement joints is, yeah, there are various standards, and you can read the NHB stuff and the LAB stuff. There's always subtle differences. But the other thing to remember is, nowadays, when buildings are not often built out of traditional materials, you know, even these stone detached houses that you see, it's not real stone, it's reconstituted stone. So you've got to think about the manufacturer, and usually the manufacturer of the actual material will have their own standards as well, which may differ from the standards you've just read, you know. And we've seen that in some of the new build interventions we've had to do, where actually they've followed the NHBC guidance, or they've followed, you know, British standards, whatever it is they've looked at. But then the manufacturer's been called in because there's been some cracking. He said, yeah, but you didn't do this. You should have put bed joint reinforcement underneath all those openings that have got a height to width ratio of less than 3:1. And you didn't. Aha. Right. So it is a complicated, there's no straight answer to it. Fortunately, we don't do a massive amount of work on the new stuff, you know, because often the builders they've dropped a problem, haven't they? So they try and fix it themselves, but that's why we get called out to so many horrible fixes. Most of the time we're dealing with houses that might be 20, 30 years old, and the proof is in the pudding. Then you can see, you know, the bed, then the movement joints out of precaution. The movement joints, their lack of them is now showing you by the cracking. You know, you're seeing that the building's making its own movement joints, you know, so we have to get in there and alleviate it. You don't always have to put new movement joints in. Sometimes just bed joint reinforcement and monitoring, you might say to the client, well, actually, this isn't that severe. It just looks bad because it's been happening for decades. So we're going to stiffen that area. We're going to give it a bit of tensile support. And then I can't guarantee you won't get any more cracking elsewhere. You won't get cracking where we've done the work. But I can't guarantee you won't get any cracking elsewhere. But let's just monitor it. And you might find you don't have to put more movement joints in. And that's a reasonable opinion to have. But a client then may say to you, no, I need absolute assurance I'm going to get no more guarantees, in which case we do the reinforcement and we do the retrofit movement joints. And then you know you covered it.
Well, folks, here, I do apologise. We are running over time here. We're close to... we are just about to finish off. In terms of kind of the questions, there is a stack of questions there that we've not necessarily been able to pose just that, but I will pass them over to Brian. If Brian does get an opportunity to get back to, then brilliant. But there is one last question, Brian, I'm going to pose because it's come via social media for me and also via the chat. And a bit light-hearted is, where did you get that brick pattern tie from?
I get these from anywhere. I've got loads of different ones. You have a close look at that. No, right not. The thing is that I wear different ones. I'm the only one in brick tie who does it. I don't know why. I think it's highly fashionable, but the staff won't be seen dead wearing one day. Yeah, but if you type brick tie into Google, you'll get my website, but you'll also get brick tie, and you can actually. I think this came from Zizzy or something. I sometimes give them out if at CPDs I'll ask a question, and the person who gets it right gets a bottle of champagne if I'm feeling flush, or a brick tie. So
well, there you go, folks. There you go. Well, guys, you heard Brian mention it earlier on, some sources of additional information. There is places you can go if you want to get further reading. It's up on the screen at the moment in time. There is a library at the PCA you can visit where there are documents such as installing wall ties and lateral restraint ties and other stuff there. There is further reading. You heard Brian mention about the Brief 361, Why Do Buildings Crack? You can also, as well, only ourselves, the Construction Fiction Association, and there are the books there that Brian referred to as well. If you are interested in any kind of further training, there are training courses at the PCA that can help you. All of our training courses now, it's 2022 that we now have available dates for. There is a prospectus coming out soon, so if it is something you are interested in, then please do get in touch. Just to kind of let you know, next webinar coming up is our last webinar for 2021. And as such, we've traditionally broken away from the last Thursday to bring it to the first Thursday in December. We haven't actually got a proper working title here, so this is a bit of a title I've made up, but it's along the line of bats, beasties, buildings and legislation, and it's all about how wildlife can affect us when doing surveys and remediation works. And this is something that affects all sectors. So certainly, please do. We hope you come along. Registration will open for this very, very shortly. It should be available later on today. So just go to that web link, property-care.org/webinars. But last but not least, I just want to say, as always, a big thank you to everyone that joined us this morning and listened. I really do hope you got some really good, valued learning from today. Brian, I want to say especially a big, big thank you to yourself for that presentation. It was excellent, really informative, and hopefully the audience agrees, and certainly going by the chat, it was greatly appreciated. And lastly, but not least, I just want to say to everyone, big thanks for joining us, and hopefully you have a lovely rest of the day. Take care, everyone.